Hello friends, welcome back. In today's lecture, I am Dr. Milind Meshram, working as an assistant professor in the Department of Chemistry, CHEM College, Nashik. In the last lecture, we have seen the stereochemistry, which can be seen in the SN1 reaction. So in the last few lectures, we have been discussing the SN1 reactions. So where we have seen the SN1 reaction and its mechanism, kinetics, energy profile diagram. Thereafter, we have seen the various factors that affect the SN1 reaction. Alright. Thereafter, we have discussed the stereochemistry. Alright. So, in today's lecture, we will discuss the SN2 reaction. Okay. So, substitution nucleophilic biomolecular reaction, that is SN2. As I had mentioned it before, this SN stands for substitution nucleophilic and this 2 stands for biomolecular. Since the rate of this reaction depends on the concentration of both the reactants. For example, nucleophile as well as the substrate. Alright. So, this SN2 reaction refers to nucleophilic substitution, in which nucleophile and substrate converted to substituted product via transition state. Alright, transition state. So it is having the concerted mechanism. Bond breaking and bond making takes place simultaneously. Okay, this bond breaking and bond making is synchronous. Alright. So it will happen simultaneously. Alright. So let us have example. Suppose we have this methyl bromide, methyl bromide is generally primary alkyl halide. Primary alkyl halide. When you treat with this aqueous NaOH, so it will generate this hydroxide ion, that is the nucleophile. So it gives methyl alcohol. Methyl alcohol. So this is our substituted product. Alright. So when you treat this methyl bromide with aqueous NaOH, so it gives the methanol as a substituted product. So as I mentioned it before, this rate of this particular SN2 reaction, it depends on both the concentration. Alright, concentration of this substrate. This is the substrate, as well as this nucleophile. The rate of the reaction, it depends on the concentration of both the substrates. If the concentration of the substrate is substrates and nucleophiles double, so rate will also get double. If the concentration of either these reactors is half, then rate will also result in half of the rate of the reaction. Alright. So it depends on the concentration. As the one of the factor, that is the collision. Collision is also important factor in this reaction. As the concentration of the substrate and nucleophile increases, the collision will also increases. The collision of this nucleophile with substrate methyl bromide increases, that means it will result in the increase in the rate of the reactions. Alright. So concentration If the concentration increases, that means collision will also get increases. So ultimately it will result in the increase in rate of the reactions. Alright. So let us have this kinetics of this reaction. Kinetics of the reaction. As I said, the rate of the reaction, it depends on the concentration of the both the substrate as well as nucleophile. So the rate expression would be rate is equal to K methyl bromide, this is our substrate, and this hydroxide ion. Alright, so this is our substrate and nucleophile. As the concentration of this both the reactor, that is substrate and nucleophile, increases, concentration increases, so collision will also increases. That means it will result in the increase in rate of the reaction. So this rate of this reaction is depends on both the reactants. Alright. So let us have its mechanism. This mechanism of this SN2 reaction involves the mechanism of this reaction involves transition state. Alright. So it is the concerted mechanism. So concerted means bond breaking and bond making occurs simultaneously. Alright. So via transition state. Alright. So we have, this is the sp3 carbon. So this hydroxide ion will attack at the back of this CBr bond, back side attack. Okay. So this bromide will get depart. So this is the slow step. So we have when this nucleophile will attack, backside attack, so this is the slow step. Okay. The overall rate of the reaction, the overall rate of the reaction, however, depends on the slow step. All right. So in the bond breaking and bond making, both these steps are slow in this concentrate mechanism. As we can see here, bond formation and bond breaking is taking place simultaneously. Alright. So when this nucleophile will attack at this carbon, then this bromine gets departed. So we can have this transition state. Alright. So this carbon is pentagon coordinated. Then this bromide gets departed. Okay. So we can get our product, substituted product. As I mentioned it in one of the lecture, when we were discussing SN1 reactions, so bond breaking is a endothermic reaction since it requires the absorption of heat, so it is endothermic reaction. Then bond formation is so that reaction is slow step, and bond formation is a exothermic reaction. All right. So since this bond breaking and bond making is a simultaneous process, and this rate of this reaction, it depends on the concentration of both the reactants. So this bond breaking and bond making, both the processes are slow step. All right. So let's have its energy profile diagram. Let's put this XY axis. So this will be potential energy, and this is reaction coordinate. Right. Delta E is the activation energy. So this will be nucleophile plus this RBr. This is reactant. And we will have here product plus the bromide ion. Alright, so this is this transition state. So this is our product. When the nucleophile attacks backside of the alkyl halide, so the bond breaking and bond makings happens simultaneously, synchronously. Okay, so it will generate this transition state which is having the potential energy, okay, high potential energy. So it gives this pentavalent carbon this transition state, this bond formation and bond breaking is happening simultaneously to then which result in the formation of this substituted product. Okay, so this bromide will get departed and it will lead to the formation of substituted products. Alright, so in the substitution nucleophilic bimolecular reaction, that is SN2 reactions, so one of the most important aspect we can see, one of the most important property of this SN2 reaction is inversion. Alright, so we will explain that property with the help of some examples. Okay, so we will see this stereochemistry. So as I mentioned it before, so one of the most important factors that deals with the SN2 reaction is inversion. Alright. There are many evidences that proves the stereochemistry in the SN2 reaction. So for example, when you have the substrate it oscillates this is the trans tosylate derivative. Alright, so when you treat this with potassium acetate, alright, so we could get this cis product. Alright, so this is our SN2 reaction. So when this tosylate derivative reacts with this potassium salt of this acetate, so we can get this cis product, because this acetate nucleophile will attack from the axial side and this tosylate group will get departed. Alright, So this tosylate in the starting material, the tosylate is at equatorial position. SN2 reaction is happening over here. So this nucleophile acetate group will attack from the back side of the tosylate, so that the overall reaction will, this inversion product we can get it. So this inversion is known as Walden inversion. Alright. So this acetate anion will get approached from the back side of the tosylate, and this tosylate will get departed, so that we will get this inversion product. So we can have another example as well. So if you take the chiral substrate, so if you start with, for example, S secondary butanol, so let's say this is plus S butanol secondary butanol. Alright. In the first step, this hydrogen group will translate it to tosylate group. So let's treat with tosyl chloride in the presence of pyridine. So since this pyridine is basic, so it will accept this proton and it will react this group. Okay, this chloride will go. Okay, so we will get this OTS. Here you can see the retention of configuration. Why it is so? Because there is no any bond breaking. So just this proton gets deglutenated and this tosyl group will get attached. Alright. So there is no any change in configuration. In the next step, this acetate will react in SN2 fashion. Alright. SN2 reaction will occur here. So this anion will get attacked from the back side and this tosylate will get departed. So we could have this product. Here you can see the change in configuration. Okay, so inversion is happening over here. So this is the SN2 reaction. So then reaction picture, we have this hydroxide ion. Alright, so this will get attacked at this carbonyl carbon and it will get open. This, then we will have then eventually the intermediate with water molecule. Alright. So we could get this. This product. So configuration is changed. Okay, so this would be R secondary butanol. So here you can clearly see this S is converted into R. Okay, even that sign is also changed. Okay, plus to minus. So when you have this chiral substrate and treatment with tosyl chloride in the presence of pyridine, it gives this tosylate. Here you can see there is no change in configuration. Further, it will react with this acetate anion in SN2 fashion. So it will give this product. So here you can see change in configuration because it has been generated after SN2 reaction. Alright. So then this hydroxide ion will attack at this carbonyl and it will generate this intermediate, and after hydrolysis we could get this R secondary butanol. So here you can see the change in configuration. So that means the inversion is the very important property in SN2 reactions. Okay, and this inversion is known as Walden inversion. So this is all about the today's lecture. In the next lecture we will see the last substitution reaction, that is SN3. Thank you.